Good morning, everyone. Today we are going to have fifth and sixth session. So we will wait for 5 minutes and then we can start.
Hello, good morning, all of you. So I think we can still wait for a couple of minutes. So are we expecting more of us to join?
No, we can start now. We can start now.
Okay. Okay.
Yes.
So I'm sharing my PowerPoint screen. So is that visible?
Yes, sir.
Okay. And yeah, so can you see changes in slides?
Yes, sir.
Okay. Yeah, thanks. So I'm actually trying to share my video. So can everyone see whatever I like video that I'm sharing? Is my video
No,
visible?
sir. No,
Yes,
sir.
sir.
No?
No, sir, I can't see it.
Okay.
So I think it will be my problem. You can ask someone else.
So what
Are
about
you playing
whether
any video?
Yes, sir. Your video is visible.
is it visible?
Are you are you playing any video? I can't
No,
see
I'm
it
not
first.
playing any video. Actually, I just switched on my own video. So anyway, I mean
Mm,
just
okay, okay. No, I
um,
can't see. I can see only the first slide. It is in the presentation mode. That's it.
okay. Anyway,
So you have started your camera, you mean to say, right?
yeah, yeah, exactly. Actually, so my laptop had like web camera. There is an issue with that. So
No problem. No
I,
problem.
I mean,
Start.
I had actually I tried to join through my phone and then switch on my video.
Correct,
Just
correct,
kind of in this online mode, what happens is that like so some X person is sitting in some Y place, and
yes,
you don't know who the person is, and there is no actually connect. I mean, so just for like
correct.
in that interest of
Yes,
the
yes.
connect, I had actually tried to switch on the video, and I was like
Mhm.
hopefully
Correct, correct, correct.
like if everyone can
Anyways, but
also.
some of us they might can see you, but I
Okay,
can't see. So let it be. You can start.
yeah, fine, no problem. So anyway, I think we can maybe we can get started in the interest of time. So yeah, so good morning all of you. Uh, so in today's session, we'll look at like more aspects of transmissions, especially like designing, like how to select different gear ratios and all. So in the previous sessions, we had looked at basically the in the last session specifically we had looked at vehicle dynamics and different vehicle performance metrics and basically relating the performance metrics to the vehicle dynamics. So how do we use the equations of vehicle dynamics to derive those performance metrics such as the gradability, maximum speed, and acceleration performance and all these things. So, so we basically just saw the longitudinal vehicle dynamics and we saw the simplified wheel slip model and uh, all those things like and the basic forces of like resisting forces and how to derive the maximum tractive force and all those things. So we'll apply those concepts now in the context of transmission design. So and so previously in the first session, I had shared an activity. Uh, so I hope some of you have at least tried that. Like, has anyone tried that activity? So you were supposed to compare that like some of the models that are available in the market currently. So which like let us say passenger cars which have both conventional and electric models, and so the activity was to basically compare them. So I'll just share that slide. So has anyone tried that activity? Anyone have they tried?
Please answer if you have tried. Please share your solution. If not, just tell him and do it today.
Yes, sir, we will do it today.
So
Okay,
you
I
will do
mean,
it
Do it
today.
today.
yeah, sure.
You will
Yeah, it
share
will be
in the.
actually helpful. Yeah, because
Hmm.
then otherwise ऐसे like सब theory हो जाएगा फिर मतलब then it will become like just I will just keep speaking like some theory, and then it will be kind of difficult to relate as well. So then this activity will at least generate some interest, and then I think it will be useful so that you can apply something. So this it was just basically to गूगल सर्च करना है कोई कार या बस या जो भी है उसका, लेटेस्ट से टाटा का स्टार बस प्लेटफॉर्म है तो उसमें लाइक इट हैज एन इलेक्ट्रिक वेरिएंट एज वेल एज conventional variant, right? So then we can get simple these information related to torque or power or whatever. Then uh, so then we will actually use this information for something like interesting as we go along. So we will uh, this whole thing like more interesting. So hopefully I hope you also find that same, like, so by this activity at least we'll be able to apply whatever that we have learned till now. So towards the end of this session today we will actually also look at an example. So maybe on the fly we can do some part of this activity, and later on you can actually go back, and hopefully in the next session we have more contributions related to that activity. So anyway, yeah, we'll start now. So yeah, so today's session we will focus on how do we select different gear ratios. So maybe we'll learn this with reference to conventional powertrains, but essentially the whole logic as such can be applied in an equivalent kind of fashion to any kind of powertrain which involves any power source as such. So it may be an electric motor or IC engine or anything that you can think of, so any prime mover, so as for that matter. So so this is in this figure shown over here. You have like the typical architecture of a conventional powertrain, where we have an internal combustion connected to the transmission through a dry clutch, and then we have a gearbox and a final drive. So, so the clutch is called also called like it's a moving off element. So because as we discussed earlier that the IC engine has a certain idle speed below which it cannot operate. So then the moving off element is like the clutch. It will the two surfaces will, like, whenever in contact they will keep sliding till the vehicle accelerates to the level such that the, like, both on the input side and output side we have the zero relative motion. Until that point the clutch plates will keep sliding with respect to relative to each other. So there is no speed reduction or anything involved. So the input speed is equal to output speed when the clutch is completely engaged. So then that does not contribute to the gear ratio as such. Then inside the gearbox, we may have like maybe three main parts. So we'll have a main gearbox which may have like spur gear or helical gear. So we have an input shaft, counter shaft, and output shaft, or some like basically different shafts on which different gears will be mounted in different arrangements so as to give certain number of gear ratios. So, and we have like synchronizers which can basically the shifter can slide those onto the gear pair which we need to engage to get that particular gear ratio. So that will be the main gearbox. So there is something mentioned over here called as range unit. So the rear mounted range unit or front mounted range unit. So these are additional set of gear ratios which we can use to get a large number of to get an overall wide operating range or like large number of gear ratios. So let us say if we have a main gearbox which contains, let us say, four ratios, and then this range mounted range unit, let us say it has two gears. So then the total overall number of gear ratios that we will get is 4 into 2. So that will be 8. So uh, so then this becomes like a more compact arrangement so that we can actually get 8 gear ratio. So like let us say we engage like the first ratio of the range unit, and then we on that with respect to that gear ratio we have 4 ratios available. Then in the second gear ratio of the range unit we have 4 more ratios available. So then in that sense, so we get 8 ratios with having just two these compact kind of sets. So the 4-speed gearbox is smaller than if we had to create a 8-speed gearbox using that the usual set of arrangement, then it would have been like much bigger. So this range unit actually offers that advantage. So generally these things are applied in commercial vehicles or off-road vehicles. Then we have this final drive ratio. So again, this is very important in commercial vehicles. So by that, like by changing this gear ratio, like this gear ratio is designed in such a way that we can we have to get a balance between the fuel economy and acceleration performance. So that's a very important metric, especially in commercial vehicles. Any questions till now?
No, sir.
Yeah, okay, fine. So we have different gear ratios between the, let us say, engine and wheel, or electric motor and wheel, whatever. So why do we have the different gear ratios? So in particularly with respect to conventional vehicles, this moving off under difficult conditions. So uh, which means that accelerating from zero speed. Uh, so let us say if the vehicle is stuck in a pothole or anything, so then we need a very high torque to get going and move it out of that thing. So then we need a high gear ratio for that. Uh, then to reach the required maximum speed, so again we need the gear ratio that will enable uh, the engine the appropriate ratio so that it is like the engine is able to propel the vehicle to that required speed. Then so these are kind of two extremes. Like one is basically having a high gear ratio so that we get very high torque, and the other is basically so that we get the appropriate ratio between the speeds so as to be able to achieve a certain amount of vehicle speed. Another kind of basis for gear ratio selection is to enable the IC engine or electric motor, whatever, to operate in its more efficient zones. So like we saw in the previous sessions, like about the fuel consumption map or efficiency map and the typical nature. So in order to be able to operate in that, so we also need to select the gear ratio appropriately. So let us say if we have this IC engine, map. So then, like the central portion is somewhat we will be looking for, and probably this speed range. So the gear ratio should enable the engine to operate largely in this zone also. So that is another basis of selection of gear ratio. So similarly, for an electric motor as well, we have an efficiency map. So probably this may be the zone where we want the electric motor to operate more. Although this may not be as significant as an IC engine in terms of like the severity of this requirement may not be that high as that of an IC engine. So the gear ratios that we select, so they should have a basically so so for they should be like enable the IC engine to operate in its best fuel efficiency zone and having a wide overall gear ratio uh, for is like especially important for like if you have passenger cars uh, with powerful engines and very low drag coefficient like more of like sports kind of utility kind of vehicles. Uh, so then for that, like having a wide overall gear ratio is very important. So having a very high, like lowest gear ratio. I mean, let us say first gear ratio should will be very high, and the ratio of the highest gear should also be such that we should be able to achieve a very high vehicle speed. So then that we are asking for a very wide overall gear ratio in that sense. So so in this figure over here, it is basically shown that for a certain range of engine speed operation, what is the corresponding vehicle speed range uh, or let us say for this case, it's like the gearbox output speed. So a certain engine speed corresponds to a certain gearbox output speed depending on the gear ratio that we choose. So here for let us say for the maximum gear ratio, the the gearbox output speed would be probably at this lower end. So we get a high torque but low speed. On the other hand, if for the minimum gear ratio, uh, we get this kind of a ratio between the engine speed and the gearbox output speed. So so in this particular shaded envelope, so we will get the corresponding gearbox output speed for a certain chosen ratio. So now we'll look at this term called as overall gear ratio. So this is basically the defined as the ratio between the largest and the smallest ratio, or basically the first gear ratio divided by the last gear ratio. In to put it simply, so this overall gear ratio, like for any particular application, it depends on what is the specific power output. Basically, that is the rated power divided by the total uh, mass that we can expect for the vehicle. It also depends on what is the spread of the IC engine, like speed spread of the IC engine, and also depends on the intended use. So, so by speed spread, so let us say like if we have the torque versus speed kind of, so this is like the minimum and maximum. So whatever is the range between them, that is the speed spread. Uh, Then, so we need like large overall gear ratios, especially for commercial vehicles, because they have a very low specific power output. Uh, so I mean that so they for a certain amount of rated power, they carry a lot of mass along with them. So we need like several gear ratios, especially more on the lower side, because they generally operate at low speeds and they need very high torque for negotiating gradients. And also like with diesel engine powered vehicles, because the range of operation, like the speed spread for a diesel engine is like smaller than that of a petrol engine. So then in that case, to get a broad range of vehicle speeds of operation, we also again need more amount of like gear ratios and a larger overall gear ratio required. So this figure shows like what are the typical uh, values in which like the overall gear ratio may lie. So we can see that for commercial vehicles, like for heavy duty trucks, we have a broad overall gear ratio range, and it's like slightly more on the higher side for these heavy duty trucks. Whereas for a passenger car with spark ignition engine, we have a much lower overall gear ratio required. This is like more of a general guideline, like it's more or less empirical data, so which may change time to time as designs evolve. So but this is like kind of a design guideline depending on the application. Typically, what are the changes which we can expect this overall gear ratio. So now we come to the selection of the gear ratios as particularly. So now how do we select the largest gear ratio? So the largest gear ratio is for the lowest gear. So this is mainly required. So are you able to hear my audio clearly? I just got a notification that there is some network issue.
Yes, sir.
Okay, fine. So I hope you're able to hear me clearly. Yeah, so the lowest gears ratio or the maximum ratio, it is determined by the maximum tractive effort or gradability requirement. So it's basically you can say that it is like the maximum starting torque required by the vehicle. So that is a metric based on which you will design the ratio of the lowest gear. So we will also need to take into account what is the maximum tractive force that can be transmitted by the tires and road. Uh, so the maximum tractive force should be limited by that. So that is a physical limit that we will put onto the tractive force. Uh, so let us say if the source, the engine or motor is capable of providing very high torque, but the tire and road contact will again have a physical limit. So whichever is the minimum among them, that we will select. So let us say if we have uh, the in this, let us say we consider that the maximum tractive torque or tractive force that is like the with the power source, that is still within the limit of the friction limit or maximum tractive force limit, which is basically the physical limit between the tire and road. So then the minimum becomes the whatever tractive torque that is provided by the power source itself. So then on the left hand side, so if you look at the second equation over here, so that is the maximum torque that is provided by the power source multiplied by the maximum gear ratio. So that is basically the torque multiplication that we get at the wheels. And so this is basically the torque. So the numerator is the torque that we see at the wheels multiplied by the total efficiency of the powertrain. So which like accounts for the energy losses along the entire drive line divided by the radius of the tire, dynamic radius of the tire. So that is basically the tractive force that we will see at the wheels. So if we equate it so that so the tractive force that is available is just equal to the tractive force that is required to accelerate at very low speed. So here on the right hand side we have the resisting forces. So the tractive force provided is so considering some acceleration. So then this tractive force that is required is minus resistance will be basically the like the mass into acceleration. And here since we are considering very low speed, so it is just starting from rest. So then we will neglect the air resistance. So if velocity is small, then v square, like velocity square will be even smaller. So then because the air resistance is proportional to the square of the velocity, so then we'll assume that let us say it is negligible in this case. So then we will get this kind of an equation. So as a relation between the tractive force available and the tractive force required. So what we will do with this relation, so we will use it um, to basically calculate what is this ratio I max, which is the ratio of the like largest gear ratio. So generally for passenger cars or commercial vehicles, we can design it like the transmission like largest gear ratio for maximum gradability. So gradability is like as we saw in the previous session, it is the maximum grade that the vehicle can climb at a certain constant speed. So let us say that the vehicle just gets moving. It's like let us say 1 km per hour speed or even probably less than it, just crawling and trying to climb a certain steep slope. So in that case, what will be the slope that the vehicle is climbing? So then for that grade or that angle alpha or of the road inclination, what will be the gear ratio that, so we use the previous equation and we find the value of this I max. So then using that this equation we can calculate the largest gear ratio. Then so this was basically the gear ratio based on torque requirement. Now in addition to that, there are some categories of vehicles which have so-called crawler gears. So these kind of vehicles like building construction vehicles or road sweeping kind of vehicles, so or some other kinds of commercial vehicles, so they move at extremely slow speeds. So then to get that speed reduction between the power source and the wheels, so then we may have a highest like large gear ratio that is required to for the vehicle to be able to travel at that speed. So let us say we have a crawl speed. So then we may also select the largest gear ratio in these cases for that crawler gear ratio using this speed. So the speed is equal to r into omega, or basically the radius into the angular velocity. So using that same logic, so then the wheel speed will be a function of the gear ratio, uh, and so the crawl speed will be r into omega of the wheel. So the omega of the wheel is basically the omega of the engine or motor. So the maximum or maybe minimum RPM or minimum speed of that engine or something divided by the gear ratio that is required. So this kind of crawler gear application is more relevant in where we have IC engines. So with electric motors, we may not really because the electric motor is able to provide very high torque at very low speeds. So then this requirement may not be as relevant, but it's probably more relevant to IC engine kind of vehicles. So now we saw how we select the largest gear ratio. So now we will come to how do we select the smallest gear ratio. So the largest gear ratio was more like dictated by the torque requirement, whereas the smallest gear ratio can be selected basis on the basis of the requirement of maximum speed. So let us say we assume that there is zero slip in the power transmission from the wheel to the road. Things are like very ideal power transmission. And we also like let us say we assume that the maximum speed of the vehicle is reached at the maximum engine speed, which is a reasonable assumption. So then the maximum vehicle speed that determines the ratio of the highest gear. So we know what is the maximum engine speed, and if we know what is the maximum vehicle speed that has to be achieved in the highest gear, so on basis of that, again we use the simple kinematic relation of the velocity is equal to radius into the angular velocity. So then, so at the highest uh, engine speed or highest motor speed into multiplied by the radius divided by the gear ratio will be the uh, vehicle speed or the max vehicle speed. So then using this simple equation which is here below, we can select the smallest gear ratio. So any questions or any doubts till this point? So let us say if we draw, like we had seen how, so for the IC engine, like how we have the tractive force versus vehicle speed kind of plot. So then, so for different gear ratios, we will get the tractive torque versus speed kind of a plot, like superimposed for every gear. So then this corresponds to the maximum and minimum engine speed. So for every gear. So then, so for the maximum vehicle speed, we will be looking at like the highest gear and at the maximum engine speed, what will be the corresponding vehicle speed. So if we draw a vertical line at this point, so then this is the point where it cuts the x-axis. So that will correspond to the maximum vehicle speed that it can achieve. So if we have a vehicle maximum speed specification, so then we can place this torque speed curve accordingly, so that we get the maximum speed at the highest engine speed in that highest gear ratio. Is that clear?
Yes, sir.
Okay. Uh, then, so we'll move to more specifics of the smallest gear ratio uh, selection. So if we say, consider like commercial vehicles, so there are limiting factors like speed restrictions, like they're like imposed by the government. So there are legal speed restrictions, like what is the maximum allowable. So on highways, especially, we have, on like Mumbai Pune Express Highway, we have like 80 kilometer per hour for like heavy commercial vehicles, and for passenger cars, we have 100 kilometers per hour. So Similarly, we may have different speed restrictions at different places. So especially on turns, we may have lower speed limits like 40 kilometer per hour or so. So for passenger cars, another important consideration for selection of this gear ratio is like so the passenger cars end up spending like more time in the higher gear. So in the highest gear, it may actually spend more than 80% of its time. So considering like extensive amount of highway driving, so that is another consideration. So if we have more emphasis on the maximum speed, so then for that we select the gear ratio appropriately. So this bar chart like shows what are the representative maximum allowable speed. So they are more. This is more relevant in Europe. So for different categories of vehicles, for commercial vehicles. So these are some representative maximum allowable speed. So we may design the maximum, the highest gears ratio based on basis of this. Now, when we come to passenger cars, so then there are different approaches that we can think of. Uh, so if we consider so in this case, let us say if we consider conventional IC engine powered vehicles, so we saw how the torque versus speed plot looks like, right? So for multiple gears. So now if we try to plot what is the tractive force, so let us say this is force versus vehicle speed. Now if we try to plot uh, what is the tractive force required at any constant vehicle speed. So acceleration is 0. So then in the longitudinal dynamics equation, so if this is the tractive force minus total, let us say resisting force, let us say R should be equal to 0. So then if we equate, so this resisting force will have air resistance, grade resistance, and also rolling resistance. So then in this case, if we equate this tractive force to resisting force, so then and if for every possible vehicle speed, if we calculate this tractive force required and if we plot that, so it comes out to be something like this, right? So this tractive force versus vehicle speed curve for the this is for the requirement basically, and these curves like here for the IC engine, they represent what is the maximum tractive force available at every vehicle speed. So now wherever they intersect, so let us say this point, so that point defines the maximum vehicle speed. So by definition, the maximum vehicle speed is generally defined for a flat road with zero grade, and so considering the tractive force or tractive power requirement on a flat road, so wherever the tractive torque available and tractive force available and the tractive force required, so wherever they meet, so that is the maximum vehicle speed that can by definition. So now similarly, if we have to construct a power versus vehicle speed, so how will that look like? So because this lies on a hyperbola kind of thing. So for a constant, like maximum power requirement is like fixed. So then let us say this is the horizontal line which represents the maximum power. So the IC engine has a power versus speed graph which looks something like this. So at a certain point, it has maximum power, and it will be zero for zero vehicle speed. So similarly, for higher, like this is, let us say, for the highest gear ratios, and so then maximum vehicle speed achievable in this first gear will be this. So for higher gears, if we try to plot this, so then it will look something again like this, for progressively higher and higher gears. So all of these curves will touch this maximum power point. And if we try to plot similarly this tractive force versus vehicle speed, so now tractive power versus vehicle speed, so then it will again be some kind of a polynomial, like it will be proportional to velocity. So this is proportional to velocity square, so it is parabolic in nature. So power is like force into velocity, so it will be cubic, so it will be v cube. So then it will probably something like this. So this is the tractive power requirement. And whereas these curves like indicate these curves, so they indicate the maximum tractive power available. So now wherever this requirement and available curve intersect, so then again that will correspond to the maximum vehicle speed by that definition. So this is again for a flat road kind of a scenario. So we can actually think of different approaches. So where this particular point should be. So this point of intersection, if we place it such that it intersects the, so the maximum power versus speed curve at, like, let us say this is the point. So if we place this curve such that it intersects this power requirement curve at this point itself. So somewhere here, let us say. So this is what is shown over here, this point A and this curve called as PZB. So that is the power requirement. And this curve is the maximum power versus vehicle speed curve. So the intersection point is A. So which corresponds to the maximum power available from the IC engine. So if we place it like this, that will be the maximum, like corresponding to that, whatever maximum velocity that is achieved at that. So let us say we call it as Vmax TH. So that is the theoretical maximum speed corresponding to the maximum power the IC engine. In addition to that, we have two different approaches called as overraving and underraving. So we'll come to that. First, we will basically look at this point. So this type of design where we make the power requirement curve intersect to the, like, maximum engine power available curve at the maximum power point, that will basically enable to convert the maximum engine power available into maximum performance. So here there are like important considerations, like so, so for a certain speed, like with this particular transmission design, how much is the like, so the tractive power requirement is for a constant vehicle speed. So for any, from like starting from a certain vehicle speed, uh, you know, by what like how much is the power available in excess at that vehicle speed, so with which we can accelerate for to further higher speeds. So that is like that is another important metric of consideration. So what is the excess power available? So so what is called as acceleration reserve. So in the top gear, so let us say if we consider like again this kind of a power versus speed curve. So if we just look at the power versus vehicle speed for like this is, let us say this is for the highest gear. So this is the tractive power versus uh, vehicle speed requirement. This is the requirement and this is what we have available. So this will be, let us say, the maximum speed. Now if we consider at a speed something lower than the maximum speed, suppose a speed like this, so then this is the power required and this is the power available at that speed. Here power required and power available are equal. So here there is a difference. So this is the excess power that is available, which can be used to accelerate starting from this speed to a speed higher than that. So, from performance point of view, this is another important consideration. So if we have more excess power available, so if the curve is placed such that we have more excess power available, then it is more suitable for a performance requirement. So in that sense, this is an important metric. So like if we carefully look at this thing, so this whole transmission design approach is like more or less tailored to the nature of the engine power versus speed kind of profile. So like if we have like consider an electric motor, we can actually come up with more like different approaches, or which may, so these approaches can be carried forward to uh, like to the design of the electric vehicles as well in a similar fashion or with certain small modifications. So let us say because this particular maximum speed kind of design, so based on maximum power point, so that is more relevant to an IC engine because the maximum power available is in a very narrow speed range. But for an electric motor, that's not the case, right? So the electric motor maximum power will look more or less like this. Like it will have a very flat maximum power available kind of curve. So it will have a very wide range over which maximum power is available. So then the power requirement versus vehicle speed curve will, let us say, intersect at this point. So then this can be defined as the maximum speed that can be achieved. So let us say if I have a multi-speed transmission, and let us say this curve represents the highest, like the top gear power versus speed plot. So then in that case, this is the maximum vehicle speed that can be achieved in that case. So on a flat road, as a like the cruise speed. So now in by that definition of excess power, so we have this at the excess power, and here in this at this speed we have this at the excess power. So if we like compare it with an IC engine, we have much lesser power available, or like at least qualitatively it seems that excess power kind of thing is like much lesser as compared to an IC engine. So can someone like qualitatively, can you tell like what kind of an acceleration behavior that we can expect, like considering like if we have an electric motor versus and conventional, so what kind of an acceleration performance? So qualitatively, how would it be? Which vehicle would you expect to be faster? What do you think?
So electric vehicles will be faster than combustion vehicles.
Someone is speaking. I cannot hear you actually.
Hello, sir.
Hello.
Sir, the electric vehicles will be faster in acceleration compared to
Okay.
combustion vehicles
Okay. Why do you think so?
because they give a maximum torque at 0 RPM.
Yeah, that is true. What can you say in terms of like this, whatever we just discussed?
Sir, in order to get maximum torque at low RPM for engines, we need higher gear ratios at the beginning.
Yeah, that is true. Yeah, you whatever you said is right. So I was just like expecting that. So this is like in terms of this excess power definition, this like let us say for the same highest gear ratio. So with an IC engine, qualitatively the amount of excess power available at a given certain vehicle speed would probably be higher with a electric motor. So we may actually expect faster acceleration performance with an electric like vehicle. So yeah, so so for that, like I was actually asking you to um do that activity so that we have a conventional more like variant and then the corresponding electric variant. So the basic vehicle is same, all the vehicle gross weight or something will be similar. So then we can actually have an apples to apples comparison between conventional and electric so that we can actually look at how the performance and uh, range and all those things change. So I would highly recommend you to do that activity so that we can actually uh, so look at different categories of vehicles and how the conventional and electric variants perform. So we looked at this approach where we place sorry. Yeah. So like how do we place the power versus vehicle speed curve, and depending on that, so with respect to the tractive power requirement versus vehicle speed, how do we place the power versus speed plot? So depending on that, we have something called as overraving design and underraving design. In addition to what like placing the maximum power point at the maximum vehicle speed. So overraving design is such that uh, if we have it such that uh, that the IC engine has to run at a faster vehicle speed to achieve the same vehicle speed. Sorry. So then so if we have this curve like this, and I'll use a different color, say this blue one. So let us say this green curve represents the tractive power required versus vehicle speed. So this the red curve and green curve intersection point that represents the previous kind of design. And the blue curve shown over here, so that intersects the tractive power required curve at this uh, part where it's on the like the power versus speed curve is on the declining side. So it is after the maximum power point. So then, so corresponding to that point, the engine is actually rotating at a uh, higher speed, so to achieve that same vehicle speed. So here we get a higher gear ratio as compared to the previous one, so as to achieve the same vehicle speed. So like if we have like consider this, so for the same vehicle speed, let us say this point, so this maybe is like this is the excess power available here. So so to accelerate from this like vehicle speed to higher ones, so this is the maximum power that is available at this. So the difference between them is the excess power. So if we look at what we have for like this blue curve, so we have more excess power in this particular like if we place the curve like this. So to accelerate from this speed, we have a higher excess power. So this can give us like slightly better performance. So by placing that, but here the IC engine has to work more or like rotate at higher speeds in order to be able to achieve like higher performance. So then the engine operating points like will shift more towards the higher speed range, and then this will have an adverse impact on the overall fuel economy. But this is like more suitable for like performance vehicles where we care more about the performance. So now if we care more about the fuel consumption, then we have an under-revving design. So where the engine speed, we will try to lower the IC engine speed for the corresponding vehicle speed. So now we have this blue curve for the over-revving design. We have this red curve corresponding to the this particular design, this Vmax kind of design, and let us say we have this. Can think of another curve which is further away from this. So then the green one is the tractive power versus vehicle speed required. So for the blue curve, it cuts the green curve at the maximum the last point of the blue curve. So that corresponds to the highest engine speed that is like allowable. Whereas it curves like cuts this purple curve. The green curve and the purple curve intersect at a much lower vehicle speed. So this point. So the maximum vehicle speed is like by definition like the point of intersection. So that corresponding vehicle speed is actually lower than what we get for this particular point. So for like this corresponding this for the same vehicle speed. So if we like have any consider any vehicle speed, so then for this type of an arrangement, so this gives us a gear ratio which is smaller than smallest out of these three, and so that the engine speed is actually much lower for considering the same vehicle speed. So then that's how the engine actually operates at a lower speed and it moves into areas of like lesser fuel consumption. So then that has like better implications in terms of fuel economy. So is this okay? Like anyone has any questions on this part? So up to this part, is it understood? So any comments, questions, anything? So I don't know. I mean, there is a long silence. So क्या चल रहा है मतलब? I don't. So please give me feedback. Like what do you think? Like whatever that is being covered. So are you aware of these all things already? Is it boring, interesting, अच्छा है, बेकार है, बकवास है, क्या है?
No questions, sir. It's interesting.
Okay. Okay. So shall we proceed?
Yes, sir.
Okay, fine. So we saw this underraving design, which is more suitable from a fuel consumption point of view. So how do we achieve this? Lower overall like powertrain ratio in the highest gear. So we can actually increase the overall gear ratio, like the ratio between the highest gear and lowest gear, or we can uh, reduce the final drive ratio, uh, and then we will actually get like corresponding lower gear ratio, like lower overall gear ratios corresponding to each gear of a multi-speed transmission, or we can increase the overall gear ratio by simply increasing the number of gears. So we can actually add another gear for overdrive. So overdrive is where the ratio between input speed and output speed is actually like less than one. So normally like in for any gear ratio, so then like gear ratios will be generally more than one. So the engine speed is rotating at a speed higher than the wheel speed. But for then overdrive kind of scenario, we have an engine running at a lower speed to get a for the corresponding wheel speed. So we'll see an example. Let us say, so if we consider a four-speed transmission, so we have four power versus vehicle speed curves. Then, so we construct this PZB curve, so which is the tractive power required, and the four power versus vehicle speed curves are uh, the power available for like different gears. So this figure A, it represents the design where we place the maximum power point, like the maximum. I mean the tractive power requirement and the tractive power available intersect at the maximum power point. Then this figure B, it shows that like if we uh, so if we reduce the overall gear ratios, so then this point like all these like this the highest gear ratio curve will actually move farther away. So then we have this underraving design like this. So then it intersects at a point lower than on this part, like instead of here. Now if we keep the gear ratios of the transmission same and we decrease the final drive ratio or axle ratio, then uh, then these curves actually will move slightly rightward. So if we compare like between A and C, then the curves are actually shifted rightwards. So the gear ratios of the transmission are same. So by just shifting the axle ratio, we can actually lower the engine speed for the corresponding vehicle speed by that for achieving the same vehicle speed. So now we have like another option to add a fifth gear. So we keep the all first four gear ratios same and we add another gear with a gear ratio, let us say less than some ratio less than 1. So then when we shift the transmission into the fifth gear, so the corresponding engine speed will be actually lower, so then that will actually be helping improving the fuel consumption by operating the engine in a lower speed. Okay. So we saw how we select the highest and lowest gear ratios. So now how do we select the intermediate gear ratios? So there can be different approaches over here. So this actually depends on our objective. So one guideline can be that we place the intermediate gear ratios such that so let us say this is the maximum power. This curve represents the maximum power versus like rated power. So the torque versus speed variation for the uh, rated power. So on a torque versus vehicle speed, this will appear something like this. So we try to, if we try to place the gear ratio such that this torque resulting torque versus speed curves will try to closely approximate this hyperbola. So then that will actually be beneficial in terms of fuel economy as well as performance. So this intermediate gear ratios will be, we should select them such that, they will enable the engine to operate in its best fuel efficiency zone, or for an electric motor in the best efficiency zone correspondingly. So we can think of an approach like this. So let us say that if we select the gear ratios such that like the steps between different gear ratios are equal. So this plot over here shows the vehicle speed versus the engine speed. So if we have the gear ratios placed such that they allow so they correspond to the same range of operation of the engine for different ratios. So then let us say in the first gear we have first gear is already known since we have selected the largest gear ratio, and highest gear is also fixed here since we have selected the smallest gear ratio. So let us say if we have 4 gears. So now if we uh, place the gear ratio such that the ratio between successive gears ratios are equal, so then that is somewhat of a geometric progression kind of thing. So then ratio of the first gear to the second gear is equal to the ratio of the second gear to the third gear and so on. So let us say we call that as kg as the ratio. So then by the geometric progression, so we can let us say if we have want some n steps, so then this kg we can derive it. So if since we know this ratio of the first gear and the last gear, so how many steps do we need? Based on that, we get the corresponding factor kg, and then we can calculate uh, the intermediate gear ratio using this approach. So is this okay? Like is this understood, this particular approach?
Sir, are we choosing this to be equal in ratios just so that it is easier to decide the gears, or is there other particular
Yeah,
reason for that?
yes. So yes, you're right. So we will keep the engine speed of like speed range same. Like let us say, so the minimum and maximum speed ranges we will keep it same, and this may actually like finally our objective is to be able to achieve max like so the rated power available, like the gap that we see between these, like there will be some points where the engine will not be able to provide power. So at this, like this is whatever I'm shading right now, so that is the gap that is created. So finally we have to look at that, so there should be as less gaps as possible. So there, so that can be achieved by having more gear steps. So more and more like gear steps that we have, then the gap will become smaller. So if we just place like let us say two gears between this, so like the same hyperbola, if we place this just two gears, then there will the gap will be larger. So as we go on progressively increasing the number of gear steps, so then the gap will be smaller. Uh, and this can be a simpler, this is like a just a initial kind of like once you start the design, you can start with something. So we can just select it in a way so that like we consider the same engine maximum and minimum speeds for every gear, and we select the ratios so that uh, we get the same ratio between them. So that may be a simple approach to start with. So later on, we have to finally look at like we can keep doing iterations so that we try to minimize this gap between this whatever can be achieved and whatever we expect. So it's kind of a starting point approach
Yes,
in
sir. Okay.
gear ratio selection. So so I think we have like till now we have seen like different like approaches, like how to select the largest gear ratio and the intermediate gear ratio. So I recommend that we actually so has anyone actually been able to extract the like information that I shared, like the activity part? So comparison between the uh, conventional and electric model. So maybe those who joined later on, so have any one of you tried that activity which I shared in the first class? So we'll try to apply these learnings for that in that context. Anyone has any anything to contribute on that? So has anyone done any comparison between conventional and electric model of the same vehicle? So if not, then we can actually just try one example, and then you can actually try it yourself later on in the the next few sessions. We will discuss on that. So so please respond like what do you have anything to contribute? Like, anyone has done that? So I assume that no one has
Uh,
tried it. So
so we can do an example here, and then we'll try to do that for another vehicle in a similar manner.
Okay, fine. Sure. So I propose this example. Let us say if we have seen all these vehicles around, so Tata Nexon. So we know that we have conventional as well as electric variant for this particular model, right? So we have a petrol as well as diesel as well as electric model. So so I just made this table and I tried to fill it up like just quickly whatever like on the just like whatever information that I could get on the internet, I just put it in this table. So what I recommend is that we'll spend the next few minutes or so on this activity. So first we will try to fill up this table as much as possible. So we have some fields already filled up. So what you can, so we will take next 10-15 minutes or like let's take 10 minutes. uh, you can just check this thing like, so I have selected the Tata Nexon base model. uh, so the base petrol, so they have different variants, right? So petrol with a manual transmission, AMT, like basically automated manual transmission, electric, then we have a diesel manual and diesel AMT. So these are different, like 5 different models. So there are some fields which are actually left empty. So if you can just help me fill up those. So some things are already available, some things are yet to be filled up. So maybe we can just spend the next 5-10 minutes, and as we get like more and more information, so you can just update me so that we can just fill up this table, and then we'll move on to the next activity using this information. Is that okay? So
Yes,
you
sir.
can also cross check, like if I have if whatever information that I have put into this sheet is wrong or so, you can correct me, and then we'll use this information for a further small activity. So we will spend the remaining lecture on this activity itself. So as you said, we'll do some activity today, and then later on we can try out based on this later. Is that okay?
Yes,
So
sir.
you can maybe take the next 5-10 minutes, and like as in how you get the information, you can just immediately tell me, so I can just fill it up in the table, and we'll update, like we'll just complete this sheet. So, so whatever I was able to get, I just put it in this table. So if you get a different value or so, if you don't agree with this thing, then you can like, tell me so that we can correct it. So you can start, like you just you can just search it on the internet or something like that, and then let me know what you get. So has anyone found any information like additional in addition to whatever I was able to find so that we can just add?
Sir, instead of gross weight, curb weight is available.
Yeah, fine. Okay, fine. So we'll okay.
So for diesel manual,
Mhm.
it is 1306 kg.
0,
06
0, 6. Okay.
for uh, petrol base variant, 1237
Mhm.
kgs.
1237.
Yeah,
Okay.
for
Manual.
manual. For
Okay.
automatic petrol, again it states the same. I'm not sure if we should quote this information. It is available on 91vehicles.com, not the official website, 91wheels.com.
Yeah, it's okay. Like, I mean, कुछ भी चलेगा. Like we just have like some information to start with, some representative figures. Like it's okay. We can assume. So anyone, if anyone is able to find, so for now we will assume AMT and manual are same weight.
Yes,
Uh,
sir.
it will probably be slightly different, but it's okay. Like for now we will just assume. So anyway, update on maximum speed or anything or acceleration performance, was anyone able to get any information on that? Or any information on gradability? So I think I found this 34% on the official website. So maybe you can take like the next 2 3 minutes more and then we will So any further updates? Anyone is able to find any more information? Maximum speed, acceleration, performance, or gradability, anything?
That for petrol manual, they are stating 0 to 100 in 11.6, but some website is stating tested as 13.01.
Okay. Petrol manual.
Yes, sir.
And you were saying 11. 11.
Uh,
Okay.
yeah, 11 as official figures, but 13 as tested.
Okay. Fine. So then we'll go with 13 actually.
Okay.
Then yeah. Anyway, I think so. We can continue this later on. So you can note down all these things like for now, and then in the next session we'll continue with this activity. So for now we'll just proceed with whatever we have. So I found this Tata Nexon has gradability 34% as per their website, right? So what we will do is, so we know like this gradability specification, and from this sheet we also know what is the maximum motor torque, right? We know what is the curb weight. So then gross weight we will calculate. Let us say we will assume 4 passengers are sitting, and so let us say 4 human beings. So उसका average weight कुछ ले लो, then 4 passengers plus that curb weight. So then that will be the total weight. So you know the mass. Then so you have to find the maximum gear ratio using this gradability specification. So I hope you have noted down the equation for calculating gradability, which we previously discussed. And we will also try to find out the minimum gear ratio based on this vehicle speed specification. So let us assume that maximum motor RPM is 10,000. So nowadays we have like very high speed motor, so 10,000 may be a reasonable approximation. We actually have even higher than that. So let us say we assume 10,000 in this case. Then we will get maximum and minimum gear ratio. Then we let us say we have a 4-speed transmission. Then try to calculate the gear ratios with that, let us say, geometric progression approach. So if you are able to propose some other approach which is like more useful than that, then that is more than welcome. If you have some other logic of calculating gear ratio, if you know. So we have to basically come up with 4 gear ratios. So this activity will what we will do is we will consider like since we may not get full data or whatever, but we will try to use this information to sort of come up with some of these performance metrics. Like let us say we start with this gradability thing, and with this motor plus transmission combined together, we will see how the drivetrain performs in terms of like let us say we'll try to derive the acceleration performance of this whole concept, like and we will also try to see like if we run this vehicle uh, on a with a single speed transmission. So if we consider this motor along, so this like Tata Nexon EV has single speed transmission, so they have just 1 gear ratio. So let us say we have this single gear ratio, and and like we will probably assume a different motor in that case, like motor plus uh, for this which has the same rated power. So maybe some higher speed motor latest which may be able to go to 20,000 rpm or so, and then with that gear ratio, and then we choose another motor which has maximum speed of, let us say, 10,000 rpm, and then we have a 4-speed transmission which has different gear ratios. We will try to compare how they perform in terms of energy consumption and acceleration performance. So we will learn, what can be the possible benefits. So we will actually try to do this using some simulation based approach. So so we will do this activity in parts. Like, first we will just start off with these basic things. Like, let us say we'll select gear ratio. We'll come up with the 4 gear ratio. Then we will try to calculate this simple, tractive force versus speed characteristics. We will try to plot them, and then uh, finally we will try to actually, in a simulation environment, we'll try to compare them. So I'll see how this goes. So I will try to create a demo simulation model for this for you for demonstrating. So I expect, like you I like I recommend all of you to do this activity so that you can actually see, in a demonstration how these things will actually work out. So maybe we can, you can try to find the maximum gear ratio and minimum gear ratio for now, and also the intermediate gear ratios. Note it down with you, and we will actually, uh, move further in the next few sessions. So you can maybe take the next 5 minutes or so, or 10 minutes. And
Okay, so
calculate.
let them take 10 minutes. They will work on it and then they will come back.
Yeah.
Yeah. Yeah.
So I'll give you the equation for gradability. So it's uh, so this equations which I have put up on this slide, which I'm showing. So they are the equations for calculating gradability. So you can use these equations. So if you have any questions, you can ask me. So here we'll have to, so what, there are some like data which we need to assume as well. So to try to see what you can do. If you have any doubts, you can ask me. So anyone has any doubts how to do this?
Sir, are we doing this calculation for the electric vehicle, electric model?
Yeah, you can, yes, consider the electric vehicle model. So you know its mass, then the maximum torque of the motor is known. Then the gear ratio, overall gear ratio is something that we have to calculate. So we know tire size. So from the you will get some tire size in the specification. So you will have to find out what is the uh, what is the tire radius from the tire size, like tire specifications. Then so you know alpha. So alpha is the road inclination. So from the gradability specifications, you know tan alpha, right? So 34% is equal to tan alpha. So from that you know alpha. Then frontal area you might have to kind of assume based on like what are the so for a typical like passenger car kind of thing, so you can from the drive dimensions of the car you can approximately calculate what is the frontal area. Drag coefficient you may have to assume something, and yeah, so here actually you may actually neglect that, or you know for the gradability the you can like assume it negligible, uh, because like you are like calculating the starting gradability like at let us say very low speeds, then you may actually neglect that for now. And anything yeah, and about the rolling resistance coefficient also you can actually assume suitable values. So I had shared some charts, so you can actually put up that as well. Yeah, so this so you can use this chart and use the equations to calculate. So we need to basically find out this product of Ig into I naught. So Ig is the total like gear ratio, and I naught is the final drive. So we first need to find out just the overall powertrain ratio.
So here, are we assuming that no drag, so we can directly put CD equal to 0, right?
So was anyone able to calculate, or anyone has any doubts?
Sir, the
Yes.
drag is we are assuming no drag, so the CD term is not there, right?
Yeah, you can neglect that for the moment.
And efficiency of powertrain, we are assuming 100%.
Yeah, you can assume it, let us say 100% or maybe 99, 98% or something like that. Some high value you can assume.
Okay.
See, there is no unique solution to this problem. So it's a design problem. So you can have any number of solutions. I don't know what is the solution. So we will just, the solution will evolve as we progress. So you can just, whatever you do, you can just note down your assumptions or whatever that you have done. We will see what we can do with it. So you can actually also try the minimum gear ratio, that is actually probably simpler to do. So in the sense, the equations are like simpler for that. So the minimum ratio equation also have like put it up here. So anyone was able to calculate?
Sir, in the minimum gear ratio formula, is the velocity in meter per second or kilometer per hour?
Sorry, it's actually kilometer per hour. So it's essentially it's R omega, right? So here this is RPM and this is in kilometer per hour.
Okay.
Yeah.
Sir, so if we take 10,000 RPM, then the minimum ratio is coming out to be 6.38.
Minimum ratio is 6.38. Okay. Okay. Okay, fine. Maximum gear ratio anyone was able to calculate? So I think it's actually on like 11 o'clock already. So and I have a hard stop at 11. So I think we should continue this activity for the next session. And so in the meanwhile, you also work out these things, maximum gear ratio, minimum gear ratio, and the four gear ratios. And we will try to see how this evolves, like for a single speed versus two speed or four speed. Like we will see that. So I think we can stop for now. So we'll continue in the next session. Okay. So I think next session we will meet in the next week itself. So Tuesday morning is okay for you? Nine o'clock or something like that? Or you want Tuesday evening? That is also, I think, okay for me. Hello? Is I'm asking you whether the next session on Tuesday morning or evening, like, is it okay for you?
Sir, morning it's fine.
Okay. Fine, then I think we can close this session for now, and we'll meet next week.
Okay, sir.
Thank you.